Okay, in the previous video, we have seen how to reduce the parameter space of a potentially complex fluid mechanics problem using the Buckingham Pi theorem and the method of repeating variables. So now we've seen how to reduce the complexity of an experiment, but how do we go from the experiment to the real world? And this is the domain of similitude. Before we get into this idea of similitude, we define these two terms. So the first one is a model. So a model is a representation of a physical system used to predict the behavior of the actual system. Okay, so we're running an experiment in a lab, let's say in a wind tunnel, a water channel, something like that. We are using a model. So it's a representation of the actual thing. Okay, and so this could be a scale model of a high-rise building, a scale model of a car, a race car, something like that. And so using Buckingham Pi and method of repeating variables, we can come up with a dimensionless relationship of using dimensionless terms or these dimensionless pi groups, and we can express it as pi1m, so with the subscript m for model. Okay, so pi1m is some functional relationship of pi2m all the way to pi nm, where we have n dimensionless pi groups. And so now what we want to do is go from the model to the prototype, or vice versa, right? But typically we go from model to prototype. So the prototype is the physical system for which predictions are to be made. So in our first video in this chapter, we were looking at the flow over a cylinder. So in the lab, we would create a model, and it might be a scale model of a certain cylinder, which could be, a pipeline, the fork on a bike, something like that, right? And then the prototype is the real thing, right? So the full-scale physical system for which the predictions are to be made. So let's say your model could be a scale version of a race car, and the prototype is actually the full-scale race car for which the predictions are to be made. So we can assuming that the two physical systems are the same with just certain subtle differences, such as geometric scales, which might be different, certain velocities might be different, but otherwise it is the same problem, then we can also set up a relationship which says that pi1 is the same functional relationship of pi2, pi3, all the way to pi n for the prototype. And so what we say is that to achieve similarity, what we need to do is just equate the various pi groups. And so what does this mean, right? So when we're saying we want to achieve similarity, and again, what we mean by this is how do we translate the model results to the prototype results? We want to have what's called geometric and dynamic similarity. Okay, so as we saw in previous problems, we have certain geometric parameters that are dependent on that affect the dependent variables. So we were looking at the pressure drop in a pipe flow, and we saw that we had geometric parameters such as L over D, the length over the diameter, right? So this is a variable that affects the pressure drop. So now what we want to do is achieve that same geometric similarity in the prototype. Okay, so to match the model results to make prototype predictions, you would want that same L over D ratio. Similarly, you want to achieve what's called dynamic similarity. Dynamic similarity, so you'll have certain terms that are more dynamic terms that have more to do with the dynamics of the flow. One typical example is the Reynolds number. So the Reynolds number, given by rho Vd over mu, is a ratio of the inertial effects to the viscous effects. And again, between the model and the prototype, in order to translate the model predictions to the prototype predictions, we want to have dynamic similarity, meaning that we want to match the Reynolds number between the model and the prototype. Okay? And why would we want to do that? If the Reynolds number is not the same between the model and the prototype, then, then the inertial effects to the viscous effects, the ratio thereof, will not be the same between the two. And therefore, you might be comparing a very high inertia flow to make predictions for a highly viscous flow, which absolutely does not translate. Okay? So, this is how we apply similitude, is by equating the pi terms between the model and the prototype. So here we're going to look at a quick example. And what we have here, we have a thin layer of particles which rest at the bottom of a horizontal pipe. Okay? And we have an incompressible fluid that flows through the tube. And what we have here is that once we achieve a certain critical velocity v, or vc, then what happens is that the particles will start to rise inside the fluid. So we can create a model to determine the parameter space, or the non-dimensional parameter space, for this particular problem. So we are given here that the critical velocity is a function of the pipe diameter, the particle diameter lowercase d, the fluid density rho, the viscosity, the particle density, and the gravitational acceleration. And so now the question is here, for a length scale of 1/2, meaning that the length scale of the model is 1/2 that of the prototype, and a fluid density scale of 1, meaning that the density in the prototype is the same as the density in the model, what will be the critical velocity scale? Okay, so first what we would need to do, so here we're given the functional, well, it's not a functional relationship, but the dependence of the critical velocity Vc on the different variables. So again, we have several here, 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7. And so what we would do, we need to do Buckingham pi analysis, method of repeating variables. But for the interest of this video, we're going to come up with the final relationship here, or the final dimensionless relationship. And so we have 4 dimensionless pi groups. So we have the density of the particles multiplied by v d over mu is equal to some function of g d to the power 3 rho p to the power 2 divided by mu squared. We have a dimensionless length scale, so the ratio of the particle diameter to the pipe diameter, and we have a density ratio as well. Okay. Now, I would encourage you to go through this whole analysis and do the Buckingham pi theorem, method of repeating variables, and see if you can obtain this same pi relationship over here. Okay? All right. So we are given a length scale of 1/2 and a fluid density scale of 1. And we're asked to find the critical velocity scale. Meaning we're trying to find this critical velocity Vc for the prototype over Vc for the model. Okay? All right. So, when we're saying that we have a length scale of 1/2, this suggests that the diameter of the model is 1/2 that of the diameter of the prototype. We have a fluid density scale of 1, which means that the density of the model is equal to the density of the prototype. And again, this is a bit confusing because we have the density here of the particle and the density of the prototype, both which have subscripts p. So what we're going to do here is I'm going to add this subscript here. So that's rho particle to differentiate it from rho p, which is just the density of the prototype. So up here, also I'm going to change it to rho particle. Okay. So what we need to do is enforce dynamic similarity. Okay. So for dynamic similarity, here we have, this is, hopefully what you can see is that this is some form of Reynolds number, right? So we have the density of sorry, this is just the Reynolds number, not the Reynolds number of the particle. My apologies. So this should just be rho over here. So we have rho VD over mu, that's our Reynolds number here. So we want to match the Reynolds number for the prototype and the Reynolds number for the model. So we'll have the density of the model multiplied by the critical velocity of the model multiplied by the density of the model divided by mu, and this will be equal to the density of the prototype multiplied by the critical velocity of the prototype multiplied by the diameter of the prototype divided by mu. Now we are told that we have a fluid density scale of 1, so rho p and rho m are the same. So these ones cancel out. So we're left with VCm over VCp. So the ratio of the critical velocity of the model over the prototype is equal to the ratio of the viscosities multiplied by the ratio of the diameters. And so the prototype has twice the diameter of the model. So VCm over VCp is equal to 2 multiplied by mu p over mu m. So now the question is, can we find a relationship between these viscosities? And what we're going to do is that we're going to look at this pi group over here. And we're going to equate this pi group for the model and the prototype. So again, this is another dynamic similarity here that we're trying to enforce. So here we'll have G d model cubed and this will be rho particle for the model squared divided by mu m squared, and we're going to equate that to G dp cubed rho particle for the prototype squared over mu prototype squared. So we can see that if we have a density scale, a fluid density scale of 1, then our particle density scale will also be of 1, and therefore these two terms will cancel out. Gravitational acceleration is the same for both the prototype and the model, so we can solve for mu m over mu p. And that is equal to dm over dp to the power of 3/2. And this we find to be equal to the square root of 1 over 8. And the reason for that is the model is 1/2 the diameter of the prototype. We raise that to the power of 3, that's 1 over 8, and then we raise it to the 1/2. So that's square root of 1 over 8. So then we find that VCM over VCP will be equal to to 2 times mu p over mu m, which is equal to 2 times, or 2 over square root of 1 over 8. Okay, so please take note that I just noticed that I made a little mistake here. So if we go up over here to these Reynolds numbers, these should be M and P, which will lead us to M over P over here. And so we have M over P. Okay, and so then we find mu m over mu p, which is equal to square root of 1 over 8. So then we have 2 times mu p over mu m, which will be equal to 2 times the square root of 1 over 8, which we find to be 0.707. So this is our critical velocity scale. So the critical velocity of the model is roughly 70% of the critical velocity of the prototype if the prototype is twice the diameter of the model, all else being equal.